Ellie, how soon after these are done do we post them, the recordings?
Typically 2 to 3 weeks.
Okay. I had a colleague that wasn't going to be able to join today, but wanted to watch the recording. And I said, yeah, well, they'll be posted. I just didn't know how long.
Well, hello everyone, and thank you for joining us today for our sessions in the AIEI webinar series on understanding the potential revision to the performance grade asphalt binder specifications. This is session 1 of 3 in our webinar series, focusing today on the role of asphalt binders in the fatigue cracking performance of asphalt mixtures. Our speaker today is Mike Anderson from the Asphalt Institute. Asphalt Institute is a member of the AIEI team. And in today's session, Mike will explain how asphalt binder properties relate to fatigue cracking and how the PG asphalt binder specifications were developed and are used to address this issue. We can go, please, Mike, to the next slide.
Sure.
Now, before we begin, I would like to go through a few housekeeping items. Please keep your microphone muted during the webinar. If you have any questions, please post them in the chat box, which you can access by clicking chat in the meeting controls. I will be compiling the questions during the talk, and Mike will address them at the end of the webinar as time allows. In case of any answer questions due to time constraints, they will be responded to separately. And then also, this webinar is being recorded. A link to the webinar will be provided later. And all webinars are posted on the AIEI website, as well as our recent AIEI YouTube channel, which I will include in our chat box. So as I noted early on, this is the first in a three-part series, our part one that we're going to cover today. You can see over here the three different parts and the registration links. Part two will be on November 20, which we will build on today's fundamentals and discuss findings from the NCHRP 09-59 research project, including the proposed revisions to the binder fatigue parameter. And then on December 4, we will have our part three of the webinar series where we will focus on the expected impact of these research recommendations, including how any changes may affect lab operation, testing procedures, and the binder specifications. You can find the links to the slides and to the flyer for the webinars in the chat box. I just put it in there. Now, before I hand it over to Mike, I have to go through the disclaimer. So this material is disseminated under the sponsorship of the U.S. Department of Transportation in the interest of information exchange under the cooperative agreement number listed. Except for any statutes or regulations cited, the contents of this presentation do not have the force of law and are not meant to bind the public. The U.S. government does not endorse any products or manufacturers. And then references to AASHTO and ASTM standards in this presentation refer to private voluntary standards. Compliance with them is not required under federal law. With that being said, let's get started. I will turn it over to Mike to kick off the presentation. Mike, the floor is yours.
Okay, thanks, Ellie. So wanted to start, I guess, even before I get into the acknowledgements, by just telling you all a little bit of background behind, I guess, the purpose behind this presentation, what we're looking to do. You may have heard me talk about this at several venues going around, and what I thought was, it's a bit much to swallow, trying to get all this information into either trying to jam pack everything into like a 20-minute presentation if it's at a user producer group, or to do a longer, deeper dive and then expect that people are going to stick around through a 1 hour plus webinar. So what I decided to do after talking with Ellie and Tim a little bit was to produce shorter videos, if you will, shorter webinars that we could address kind of the key elements of some of these issues and dig into them a little bit deeper. So this one, we want to talk specifically about fatigue cracking within the binder specification, and then the research that's been done through the NCHRP 9-59 work. So certainly thanks to NCHRP. They had a couple different projects that were involved. 20-44 was a implementation project that was an overview project that we were involved with. 9-59, which is going to be the focus of this research, thanks to those research teams, as well as to 9-60 and 9-61, which we'll touch on maybe in a future webinar series. But certainly we wouldn't have anything to talk about if those teams didn't do such a great job in putting together research and thinking through all the details and allowing us the opportunity to revisit their work and what their recommendations are. Thanks to this cooperative agreement as well for allowing us to work on this. And last but certainly not least, thanks to our member companies of the Asphalt Institute. So what we wanted to do in this particular presentation, what I thought we would do is start off with kind of the basics behind what fatigue cracking is in asphalt mixtures, what affects fatigue cracking. It's not just asphalt binder, as we'll talk about, but it obviously has a role to play. How do the material properties of the binder affect fatigue cracking? And then a look at where we are right now with the PG asphalt binder specification and how it addresses the contribution of the asphalt binder properties to fatigue cracking. So one of the things that I try to remind folks of as we get into this a little bit, and it's a little bit I guess, humbling to think of it when you do stop to think about it a little bit. But the PG binder specification has more or less been in place. It's been developed and it was in draft form in 1993. So for at least 30 years, it's been out there as the principal specification that folks have been transitioning to and have been using. If you go back through history and take a look at viscosity grading and before that penetration grading, neither one of those were any longer than 20, 25 years before a new system was put in place. So penetration came about in about 1946, moved to viscosity grading in the early 70s. We went to the PG grading in 90s. So it makes sense that we've had something around for 30 years. Materials are a little different, tests are a little different. Maybe it's a good time for us to look at, what is the specification need to evolve a little bit? And that's really, I think, what this research, not only the 959 research, but the 960 research was intended to look at. So the first thing I did was I pulled this slide. This is actually from the training materials that were developed for Federal Highway Administration Demonstration Project 101. And this was in 1994. Federal Highway Administration, and specifically their Office of Technology Applications, wanted to have a way to be able to educate people on the new PG system. And so it started with, how does the binder specification address some of these distresses? And I pulled this pretty much verbatim from that slide deck, just because I thought it was interesting to go back and look at what did we say Sharp was doing with the superpave system, and how does that apply to what we're doing today. So fatigue cracking, when we're talking about that, it's distress in the wheel path. It's progressive damage. It usually shows up as longitudinal cracking. You can see it then progress to alligator cracking or potholing. You can see the imagery there. When we say alligator cracking, it's those, looks like the back of an alligator. And then eventually some of those pieces break out, you get potholes and that sort of thing. It is affected by asphalt binder, both the properties and the proportions of the asphalt binder, as well as the aggregates, properties and proportions, and the pavement structure. So all those things have to work together for fatigue cracking. You can have one or two of those be great and one be really poor, and you can have a problem. And I guess that's sort of the message, is that whenever we see distresses, we've got to look into the cause of those things. And sometimes it's materials related, sometimes it's design related, sometimes it's construction related. So all those things can definitely have an impact on what our actual performance is going to look like. Dr. Dave Anderson, many of you know Dave. He took this picture and used it in the image for some training that we did for our certification programs through the Asphalt Institute. And good picture of fatigue cracking on a roadway. It's a beautiful picture, except for the road looking a little bit cracked up. Fatigue cracking itself is it's a very difficult, complex type of thing to describe. There you can have bottom up cracking. That's where we see alligator cracking. But the other thing people see is the top down cracking, and that's a little bit different. So cracking is not all the same, and I think that's why it's really been a challenge for us to try to figure out how do you characterize what it impacts what fatigue cracking looks like, or what cracking in a roadway looks like. So again, this is just a little bit newer version of what we were saying. Basically, is that you're going to have asphalt binder, mineral aggregate, volumetric proportioning, and other factors that are going to happen. We'll talk a little bit more about top-down cracking, because that's usually caused from shear stresses at the surface, and that's going to where it exceeds the strain resistance overall of the mixture. That's something that's a little bit different than the traditional bottom-up fatigue cracking that we're looking at. We'll address both of those throughout this series. So a little bit on asphalt concrete behavior, or asphalt mixture fatigue behavior. Again, this is another image that we use from that FHWA Demonstration Project 101, the Federal Highway Administration National Asphalt Training Center text, if you will. And it basically was just trying to indicate, how do you get longer fatigue life? How do you get shorter fatigue life? Not that you want it necessarily, but it's kind of the converse of what you see there. And then what are some of the exceptions that you see? So really, to achieve that longer fatigue life, we're typically looking at, this is bottom up fatigue. We're looking at more flexible materials that are softer, they're less brittle. The asphalt binder plays a big role in that. And that's important, particularly if the asphalt structure, the pavement structure, is relatively thin. Reducing the strain in the asphalt mixture is really going to help out. So if you make the pavement thicker, you're reducing the strain before you get to the bottom layer. That's really going to help reduce that strain overall, and it's going to help you with your performance. As far as shorter fatigue life, it's really the converse. Like I said, you're not trying to have those things, but if you're looking at why are you having shorter fatigue life, it could be stiffer materials, it could be thinner pavements, higher stress strain levels, and that's kind of where the exception comes in, because it's that structure that matters as well, including the non-deflecting support layers. It's all well and good to have a pavement that you put down that's got a good thickness and it's got good materials and it's got the right proportions and you've constructed it properly. But if you put it down on a structure that's weak and that moves under loading, it's going to move with it and you're going to eventually develop some cracking there. So you can have an otherwise well-designed pavement ruined by nothing to do with the asphalt itself, the asphalt materials itself, but just by the pavement structure. So during SHARP, how did they address fatigue cracking? If you go to SHARP report A367, it talks about, and this is a lot of words here, but it talks about how they selected the specification criteria so that you got satisfactory resistance to fatigue cracking. Basically, within an asphalt binder specification, what you're wanting the asphalt binder to do is to do its part. You don't want it to be the cause of a failure. You want it just to do its part. It's not going to be able to overcome those weak subgrades or whatever have you. It just needs to not be the reason why the failure is occurring. And so they recognize that during SHARP, it's perhaps the most difficult challenge and how to put it together. And they talk about it first occurring late in the life of a pavement. So what that means is you've got to test the asphalt material in a stage that simulates what happens after it's been in service for a number of years. That's really at least part of the reason why the pressure aging vessel was developed, was to try and simulate that longer term aging that we were going to see in the binder, so that you could characterize, okay, what's it going to look like after it's been on the road in several years. Then they also talk about ideally that those properties include crack propagation properties as well, that needs to be included, and then noted that those are considered to be too complex for use in a specification, and surrogate properties must be selected as the specification criteria. So if you look at fatigue cracking, what they generally do is break it down into initiation of the crack and then propagation of the crack. So part of it is getting the crack to start, and then how does that crack progress? And they felt like putting both of those together was a little bit too complicated, perhaps, but if they use surrogate properties, they could relate to those. What they ended up looking at was dissipated energy. And they found that that was a valid fatigue criterion, and that's related to the viscous component of the modulus that seemed to be relevant to fatigue in both strain-controlled, stress-controlled pavements. And so they recognized that you couldn't really put thickness into it, but you could pick a surrogate parameter that would capture both of those things. And that was this dissipated energy concept. And they also recognized that a specification needed to include the pavement temperature to allow the fatigue criteria to be adjusted, and that so that it's appropriate for the climatic region overall. So that was an important piece of it. We didn't want to just do it at 25 degrees C, for instance. So what did all that mean? Well, dissipated energy, and you can see up there as they talk about it, is in a dynamic shear test is appropriately calculated as G star times sine delta. And so that's where that came from. That's why we've got this PG intermediate temperature criterion that we use on the DSR is this G star times sine delta property that reflects the dissipated energy that we have in an asphalt binder after it's been aged a number of years. They use that and relied on that in light of a number of field trials, but one of the ones that they reference is the Zacco-Wigmore test road, and they referred to Figure 22 there in the Sharp Report A367, and I thought that was interesting. You can go back and look at the Zacco-Wigmore test road, and what you'll find is there's a reference. I think I may have it on one of these slides. If not, you'll see it in the notes to this presentation. But in 1969, there was a paper in the Association of Asphalt Paving Technologists Journal, AAPT Journal, volume 38, which was called Final Report on the Zacco-Wigmore Asphalt Test Road by Zub and Skog. And in that, they looked at this test road that was placed into the 50s and monitored going into the 60s. And they looked at this and they found that there were, two main types of failure that occurred during service life on the project. First was fatigue cracking, and they said that was the most prevalent overall. And that was related to recovered asphalt binder stiffness. And so at least a large part of that, the consistency of the recovered asphalt binder was related to the dissipated energy, or G star times sine delta. So from that standpoint, they looked at that parameter and they said, okay, that's the reference for, what we're going to look for in a fatigue parameter within the PG system. The other part of that was not something that was directly addressed, I'll say, but it was recognized, and that's that they also had block cracking with raveling. And that was more prevalent in the passing lane. So fatigue cracking happened in the driving lane, where you would expect it. That's where the traffic loading was. But in the passing lane, where you didn't expect much traffic, they found that what they saw was block cracking with raveling that was due to a gain in shear susceptibility during weathering. In other words, it aged, yet lost its ductility during that aging, and so it lost its viscoelastic behavior, and they ended up with some block cracking that occurred. That specifically, that second distress wasn't really addressed, and not directly. I mean, it probably was tied to the G star times sine delta, but we'll talk some more about that and what that means, not only in this presentation, but also as we go into the next couple of presentations going forward. If you look at the referenced report where they talked about the Zacco-Wigmore test road and using dissipated energy, these are the figures that you can get out of that report. And figure 13 on the left is from the Zub and Skog paper, and on the right is from the A367 report from Sharp. So the 1969 paper on the left-hand side, what it is highlighting for us, let's see if I can get the pointer to come up here for us. What it's highlighting for us is this is a recovered penetration at 97 months. So that's, what is that, about 8 years, I guess. So after 8 years in service, this is what they've got with recovered penetration. And they plotted it versus percent cracking in the travel lane. So again, this is in the lane where most of the loading was. And then they fit this curve that came down through it. And where they were looking at 10% cracking, this is kind of their failure criterion. That's how they established what that recovered penetration value was. Well, in this figure over here, they took those penetration values, converted them over to G star values and G star sine delta values, and looked at the same 10% criterion, and instead looked at what a proper limit might be for controlling H hardening and fatigue cracking. And they set that originally at 3 megapascals, and that eventually got changed to 5 megapascals, or the 5,000 kilopascals that we're used to seeing in AASHTO M320 and AASHTO M332 for S-grade binders. What they further did was then take that information and validated it in mixture testing in the laboratory. So they had the hypothesis. They went to work that was done at the University of California, Berkeley, under Professor Monosmith. And they conducted a number of fatigue experiments based on the flexural beam fatigue test. We'll talk a little bit more about that, but it was what they called an 8x2 experiment. So they used the 8 core asphalt binders from the AASHTO materials reference library. And those were a wide variety of materials. We'll see what those look like on the next slide. They used 2 aggregates that had different gradations and different types of materials. One was a Maryland limestone that was low absorption. The other one was a California graywacke, which was a sandstone, and they were designated as RD and RH, if that matters to you. 2 different air void levels, 4%, 7%, 2 different applied strain levels at 400 microstrain and 700 microstrain. Those specimens were compacted. They were to get beam fatigue, they were compacted using rolling wheel compaction in the lab. And then they cut the slabs out, and then they were proceeded to test them. These were the asphalt binders that you see there. These are the references, different grades. They had different intermediate temperatures when you looked at what the intermediate temperatures were. But all the testing that they were doing for flexural beam fatigue was at 20 degrees C. So even though they all had different sort of performances, at 20 degrees C, they were all going to look a little bit different in terms of what their G star times sine delta value and what their relative stiffness was. So if you just looked at it that way and you looked at the intermediate temperatures, binder AAA would be the softest overall because it had the lowest intermediate temperatures. AAF and AEG would be the hardest because they would, or the stiffest because they would be expected to have the highest value overall. Couple of other things, I guess, to note, is this is just to give you some insight into what that looks like. These were after PAV aging. However, they didn't do long-term aging on the beams. They just did short-term mix aging. So there was a little bit of difference overall on what they would be, but at least you can get an idea of what the aging profiles might look like. This is flexural beam fatigue. So you're creating these beam specimens overall. They get loaded in the fixture that you see there. It's 4-point bending. This was discussed in the literatures in the 1950s by Professor Monosmith, Dr. John Epps, intended to simulate repeated loading that you would see in a pavement that would get cracking that would typically be bottom-up cracking overall. On the left, it's the apparatus. It's 63 millimeters wide, 380 millimeters long, 50 millimeters thick. You got the inner 2 clamps move relative to the outer 2. So the outer 2 fix it in place, the inner 2 move back and forth, and that's at whatever applied strain you're putting on it. So you can see what the beam looks like after it cracks. You develop micro cracks and then ultimately cracks that occur in the specimen. We've just used a red paint pen to kind of highlight what that looks like within the specimen itself. It does require a rectangular beam, excuse me, so it's not something that we used routinely with our gyratory compactors. We don't make those specimens. Excuse me just a second. So how do we analyze this data? In the original version of the procedure, it was defined, failure was defined as whenever you reached a number of cycles that where the stiffness dropped to 50% of the original stiffness. That's how failure was defined. It was called N sub F. It was not necessarily, it was really based more on unmodified asphalts, I guess, than certainly on modified asphalt, but it was believed to represent the point where microcracking would develop into macro cracks, and then you would eventually cause the stiffness to drop more dramatically. It did seem to work reasonably well for unmodified materials. as we started using more modified materials, as different types of materials came on the market, it was not necessarily representative. And some work that was done by Dr. Jeff Rowe with Abitec and I think Dr. Mark Bolden, who may have been with Coke or Shell at the time, I'm not sure which, but they did some work where they looked at defining a new way of what's a new way of defining failure. And it has to do with the point where the product of flexural stiffness times cycles was a maximum, and that indicates the onset of cracking that would occur. That if you plot that against the traditional way of looking at it, for unmodified asphalts, it tends to be right around 50% still, but for modified asphalts, it does a much better job of characterizing that material. And this is all just background information to kind of tell you about what they did within Sharp to validate what that G star sine delta parameter was. So ultimately, this was the type of graph that was produced. There were a number of these graphs that were produced, but this gives you just a look at it. And what it is in this case, fatigue life is here on the y-axis. G star times sine delta is on the x-axis. This is after thin film oven aging, very similar to RTFO. And that's appropriate because the mixed specimens that were produced were after short-term aging. I think they were 4 hours at 135 C before they were compacted and then tested overall. In this case, this is just the one aggregate. So it would be the Maryland aggregate, 7% air voids. They're all 8 different binders. They were done in replicates. And the blue that you see here is at 400 microstrain, and the red that you see here is at 700 microstrain. And correlation's not perfect by any means. You don't really expect it necessarily to be, but they do both show the same trend, and that's that as you get to a higher stiffness in the binder, the cracking resistance goes down. The other important part of that's something that we always talk to folks about. You remember when I said at the beginning, it's not all about the binder properties. You just want them to do their job. And part of it has to do with the pavement thickness. What affects strain in the asphalt mixture is the thickness of the pavement. So in the blue cases up here, that's a lower strain. That would represent thicker pavements than what you see in the red, which would be thinner pavements and a higher strain overall. So part of that, I say, part of it is to say that if you looked at these, you get a whole lot of bang for your buck just by reducing the strain in the pavement itself, even more so than what you can get out of the mixture stiffness and how that changes, and as a result of how the asphalt binder stiffness changes. So both of them have a role to play. I don't show the 4% air voids in here, but obviously that has a role to play as well. So all of them do matter. I think not just the stiffness of the binder, but air voids is going to matter. The aggregate itself and the combination and the packing is going to matter there, as well as the strain that you get within the mixture. So ultimately, this is what led us to AASHTO M320. The intermediate temperature parameter here, the DSR G star times sine delta after PAV aging. That's our intermediate temperature for cracking fatigue. Some of the challenges that we had early on, you saw high variability in the DSR, particularly at that intermediate temperature. And this was what was reported originally, some of the first, I guess, proficiency sample programs from AASHTO Resource, where they looked at between lab variability for G star times sine delta being at 40%, which is quite high. So to put that in perspective, if you will, you could have a lab that had a 3,400 kilopascal value and another lab that would have a 5,100 kilopascal value, and those would be considered within acceptable tolerance. So they would be considered statistically the same. That's not something that folks feel comfortable with, which means that if you're trying to produce a material, you want to make sure that you're building in for that variability. So you have to kind of adjust for that when you're making your production. And that was a concern, obviously, in what that looked like. Now, through time, through training, through better equipment, all that sort of thing, the variability has reduced, and you can see it's now down. More recent precision values are at 27.4%. That's better. It's still some variability, but certainly better than what we saw originally. But that led to some of the concerns about, well, how do you have something a little bit better? And ultimately, that's where this came into. This was a revision that was suggested through the task force of the Asphalt Institute Technical Advisor Committee, along with some work that was done within the expert task group, binder expert task group, to look at intermediate temperature stiffness, what the phase angle would be, and how might you allow something that seemed a little bit stiff, but otherwise seemed to have good viscoelastic properties. And that was through the use of phase angle, a minimum phase angle overall. There were a lot of things that were looked at to try and reduce the variability. That included using the larger plates, reduce strain levels. Those were all things that were being done. But because we couldn't lower the variability through changing test conditions, it seemed appropriate. Well, how do you adjust it then to maybe account for the fact that you've got a binder which has a little high stiffness, but its phase angle is still pretty good, indicating that you've got good performance and what should be better relaxation. And that's what led to this proposed change that ultimately got adopted in AASHTO M 320, the 2023 version. So let's go to NCHRP report 673. This is in 2023 or 2012. This came from NCHRP 9-33, which looked at mixed design and a commentary on how you make changes. And what they noted was that intermediate temperature stiffness of the binder is one of several factors affecting fatigue cracking. We've talked about that. They did say it was top-down cracking was an important distress, not just the bottom-up fatigue cracking, particularly as you looked at overlays and things that we saw and in thicker pavements. It was not a distress that was completely understood, but binder stiffness was at least a contributing factor, and that the PG system places that maximum limit on stiffness after simulated long-term aging. It does serve to limit age hardening of the binder and potential for long-term top-down cracking. But they also caution that if you really were going to look at bottom-up alligator cracking and top-down cracking and longitudinal cracking, you should take a look at a complete analysis using the MEPDG, and noted that it's more sensitive to traffic, subgrade support conditions, pavement layer thicknesses, possibly than even to the HMA properties. So again, what we were looking at is we're looking at controlling or mitigating the impact of what the asphalt binder, what role the asphalt binder has to play and what fatigue cracking is going to look at. So our learning objectives overall, we wanted to know what is fatigue cracking in an asphalt mixture. We talk about that as being repeated loading from traffic that results in longitudinal or alligator cracking. It's tensile strain at the bottom of the asphalt layer that exceeds the strength of the mixture, and that's where you get cracking that propagates to the surface. If you're talking about top-down cracking, it's caused by excessively age-hardened asphalt. So what affects fatigue cracking? Mixture stiffness, which is a function of in-place air voids, the volume of the asphalt binder stiffness, and age hardening. That may not even be a complete list of what affects mixed stiffness, but certainly those are key factors in what the mixture stiffness in service looks like. The applied loading is going to affect it. How much traffic you've got on it, how heavy is the traffic, so what's the strain that's being transferred down to the bottom of the layer, and what's the temperature? That's going to matter as well. It impacts the stiffness, it impacts what that strain is going to do. And then the asphalt layer thickness as well is going to matter. Those are all going to play into it. How do the material properties of an asphalt binder affect fatigue cracking? Stiffer asphalt binder after aging can lead to increased cracking that we see in thinner asphalt mixtures in particular. And then the last thing we talked about in the learning objectives at the beginning was how does the PG asphalt binder specification address the contribution of the asphalt binder properties to fatigue cracking? We want to limit the stiffness of the binder through the use of the dissipated energy parameter. That was G star times sine delta. That was determined after aging at intermediate temperatures that were appropriate for the asphalt binder grade and the climate in which it was used. And that specification limit that was in the PG system was based initially on the observed fatigue cracking that they saw largely on the Zachar Wigmore asphalt test road with recovered asphalt binder properties after 8 years in service. It was validated in part through the laboratory experiments that were conducted during SHARP. And ultimately, that's how they came to choose what that parameter was that was used within the current version of the PG system. So what's up next for us? It's really understanding what the NCHRP 959 research findings were, what they have proposed as specification parameters to replace G star times sine delta as a fatigue parameter for asphalt binders in the specifications. We'll talk a little bit about their findings in the next presentation, and in the following one after that, we'll talk about the recommendations and what the impacts are overall. With that, thank you very much for your attention. My contact information is on the screen. I will turn it back over to Ellie and happy to address any questions if we have time to do so. Thank you.
Sure. Thank you, Mike, very much. Thank you for sharing, such great background information. I believe this sets the stage and, get us excited about the part 2 and part 3 of the webinar series. With that in mind, we have a few questions for you. I think we have some time to go over some of the questions. And if the participants have additional questions, please continue to post them in the chat box.
Yeah.
Starting with, I believe if you go back to slide number 11 on your presentation,
yeah, let me start sharing again. I can do that.
So while waiting for Mike to share the slides, also we did put in the chat box a link to a brief survey. If you can please, once we're done with this webinar, to take a few few minutes just to answer the questions. It will help us to do better on those webinars, and we'll keep on improving with time. So please take the time. It's in the chat box. There's a SurveyMonkey link for you to visit. Do you want me to share my screen?
No, I need to reshare it because it's not it didn't pop up right. So let's see. There we go. Now it should be working. Okay. Which slide did you say?
I think it was slide 11.
Okay.
When you were showing the relationships of the penetration with the cracking, and then the G star sine delta.
Okay.
We don't see it on the screen. We still see the
You're
work.
not seeing anything.
Well, we're seeing the workshop flyer.
There we go.
There you go. Now it's moving.
Okay.
It's advancing. Yep. So a couple more, I guess.
Okay.
The question is, what was the depth within the pavement for the recovered asphalt binder? And does this imply that the specification that was developed based on this information is for near surface binder characteristics?
Yeah, that's a great question. I don't know that, and I'd have to go back through the report to see what the depth is. My guess is they probably took conventional cores out of this roadway and then they recovered it, which would have meant they used the entire depth of the layer that they were looking at. So my guess, I'm not going to say this is definite, but my guess is they're looking at the entirety of probably maybe as much as a 2 to 4 inch layer that they would be recovering. And you're going to see definitely higher stiffnesses as you're closer to the surface than you would see as if you're further down. And that's why oftentimes when we're doing forensic analysis, you probably get a good representation of how the material ages overall by doing the combined amount. But if you wanted just to look at near surface aging, we'll typically cut it within the next, within the top half inch or thereabouts, or top 12 millimeters of the surface, just to take a look at what near surface aging looks like.
Very good. Fair enough. The next question, actually, there are two questions, but I think they are interrelated. So can you explain how the grade bumping for the low temperature is handled when recycled asphalt pavement is used? And can you share your perspective on the future of large strain fracture testing?
Sure. So I'll address the last, I guess I'll start with the last one first, the future of large strain testing. So one of the original PG specification when it came out of Sharp had a larger strain test built into it. It was the direct tension test. And it came about because everything that was within the PG specification was in the small stress, small strain region. So it was in the linear viscoelastic region, and the researchers recognized that there wasn't really a failure type of test, not a larger strain test, as was mentioned. We tried to get the direct tension test to work. There were some challenges with it procedurally. There was some challenges equipment wise, and this all went through, in the 90s and into the 2000s with the ETGs, the early ETGs. And I think if you look at even AASHTO M320 table 2 still refers to using the direct tension. It's still in M320 table 1, but to my knowledge, most people don't use the direct tension test. It may still be there as a qualifier that some people use, but most people still don't use it. Ideally, if you're talking about cracking, having a larger strain test that takes it to the point of failure would give you good information. We don't have that within the equipment and within the models that we have now. I think the future of that could be, yes, we could see some of that used, larger strain, larger failure strain type of tests. The caution that I would put out there is that people don't love the variability that they see on the PAVDSR as it is right now, and that's in a smaller strain region. Anytime you're going to larger strain tests, variability is going to shoot up. It's just natural. So you have to kind of be willing to accept that if you're going to include it within a specification, is just building it so that you're not making it impossible to consistently be able to meet the specification. For now, I think mostly what we use are surrogates that we believe are related to things that will lead us to cracking. And that's why some of these parameters are about, is they're kind of surrogates for what we would expect to see for cracking. The other question had to do with bumping, I guess, of the low temperature grade for RAP.
Yes, low temperature grade, and in general, if you've seen, observed changes in the binder blending dynamics, and that has any influence on the fatigue cracking thresholds.
Yeah. So what happens, when you're using the materials, you're going to see some blending that's going to go on for sure. In a lot of cases, there are folks that have suggested that we're using intermediate temperatures in some cases that are too warm, maybe for the climates that we've got. So for instance, if you're in a PG 58 minus 28 climate, if you look at the intermediate temperature, that's used, you might say, well, that's a 19 degrees C intermediate temperature, and that may be appropriate for your climate. Maybe that's what the actual intermediate temperature is. If you elect to use, like, say, a 64 minus 22 instead, then what you're choosing to do is using a stiffer material. But because of the way that we have the specification set up, that means we're characterizing the asphalt binder for a 64 minus 22 at 25 degrees C. So in reality, you're putting in a little bit stiffer material at intermediate temperatures. You're not only putting in a stiffer material at high temperatures, but you're putting in a little bit stiffer material at intermediate temperatures than what maybe your climate would call for. And I think that's kind of the challenge we see whenever you're doing blending, whether it's with wrap or whether you're just doing bumping because of traffic loading or something along those lines, is making sure that we're capturing really the environment in which we're intended to operate. And I think that was one of the nice things about M332, which uses Masker, is the understanding that really, for many of us, we're not living in climates that are 76s, but we're still using 76 minus 22s. Kentucky, for example, where I live, on an interstate, a PG 76 minus 22 is common. It doesn't get anywhere near as hot as 76 degrees in Kentucky, but that's what the binder is that we're calling for. If you're using M332, that becomes a 64E, and that changes what your intermediate temperature is. And so that's the way we kind of mitigate what some of that looks like, I think. Hopefully that answered the question. That may have been a long-winded response to not what you were asking.
Well, I think it does, and maybe that's get us to the next question. Is basically now, given that the binder formulation have changed over the last 20 years, do you believe the current specification is still appropriate for capturing the binder's impact on the mixture performance?
I think that's what these research projects have been looking at, and I think the specification was definitely an advancement that we had when it came about in 1993. It enhanced our understanding. It gave us tools for longer term aging and low temperature testing that we just hadn't had before. But I think materials are different now. I think not only we've got different modified materials, we have other products that have been used. We've got different crude sources, even blending of materials. You saw the MRL binders we talked about. Those were single source crude binders, and I just don't know how many of those asphalts you'll see today. They might be blends of different materials, and so it's appropriate that we take a look at the specification and see, does it still make sense? And if it doesn't, what kinds of things do we need that are going to help us to understand how to mitigate the impacts of what the asphalt binder looks like on some of these distresses.
Yeah, and that being said, given that the fatigue cracking is a mixture level properties, then what specific binder properties beyond the PG system would be most critical to investigate for improving fatigue cracking resistance? And then if I want to also maybe extend that, how does the binder specification fit within the balanced mix design framework?
Right. So I think in general, going back to so I'll go back to the slide is it back or forward? It might be forward here. Yeah. So I'll go back to this slide because this is one that I lean on. The PG specification, which was based on G star time sine delta, was not, a lot of people from the very beginning didn't really love that. That G star time sine delta, they found some reasons and why it didn't correlate with some cracking that they saw. But the problem is cracking is really complicated. I think in general, looking at the stiffness of the material, if you just look at fatigue equations in general, the stiffness of the mixture, which is affected by the stiffness of the asphalt binder, the stiffness of the mixture has an impact on what fatigue cracking looks like. The binder has a role to play with that. What we don't know, and based on what we'll see in some of these future presentations, I think maybe the next presentation, is that a good enough parameter? Does that capture the not only the stiffness of the asphalt binder, but does it adequately capture the contribution of the viscoelastic nature of the asphalt binder to the performance? And that's partially, I think, where the research in both the NCHRP 9 dash, well, mainly in the NCHRP 9-59 research, that's what they were looking at is it good enough? I don't know that it's bad. As you can see, this is what some of the data tells us, but I don't know if it's quite good enough. And that's where I think without getting too much into that other presentation, I do think there are some other options for us.
All right. And then there's a follow-up question. During SHARP, was there resistance to initially adopting the R value shape parameter as a fatigue specification? This is a historical question. I don't know if you have the background.
Yeah. So I can only tell you anecdotally, but what I've heard in talking with Dr. Dave Anderson, because Dave shared with us some, I think they looked at the R value of materials and did consider that within a specification format. Dave Anderson and Don Christensen actually have a very good paper in AAPT from 1992, which talks about doing master curves and what do R values look like, and they looked at the MRL binders and that sort of thing. So the principles were there for us going way back, but at that time, I think the thought was that if you were going to put a specification together that had R value in it, you had to do temperature frequency sweeps, you had to do shifting, and you had to do modeling. And they felt like, I say they, I mean, generally speaking, the folks that ultimately came to the consensus on what the specification should look like felt like that was a little bit complicated for an initial specification. That just looking at the parameters that they identified, would be an improvement, over what was existing with both the penetration and viscosity systems. So I know it was out there. I know it was probably something that was considered. As a matter of fact, many of the things that we talk about nowadays, even if you've heard us talk about relaxation and other things, those go way back. I mean, way back. I mean, they were thinking about it during the Zaka-Wigmore test road. Hukelum talks about it in their work with Shell, back into the 50s and things along those lines. So it's not new information in many cases. It's just, in a lot of cases, we have better tools now. We have better ability to both determine these properties and to analyze what they mean.
Very good. Thank you, Mike. Another question maybe also could be related to this because you brought up mixture stiffness. But we often, discuss the stiffness, but this can arise from obviously different factors. It could be due to the oxidation, but also could be maybe due to higher density.
Right.
How does the specification account for these different contributors to stiffness, or it doesn't?
It doesn't, because what you're working with is a binder specification. So as John D'Angelo reminded me many times, he goes, "This is a purchase specification." What you're trying to do, it's a little bit like, if you're, and this, it's always suspect to do analogies, so I apologize if this doesn't quite make sense. But to me, it kind of makes sense. Like, okay, if I'm building a television, I want to make sure that I've got good components that go into that television, but ultimately it's the television performance that I care about. So from an agency standpoint, from an industry standpoint, what they want is they want to make sure that the asphalt binder can do its part, that it's not going to be what's the cause of the failure. If you take a mix, and we used to mention this all the time when we were doing training early on with super pipe mixtures, we would talk about gradations and the importance of coarser aggregate structure and that sort of thing. But we would tell people, you can take a really poor mix and put an asphalt binder in it that's a pretty good asphalt binder. Maybe it's a premium asphalt binder, like a modified material, and not roll it out on the roadways. And it's going to have a hard time performing, probably, because you can't just do one thing and hope that it's going to succeed. So part of the challenge with constructing material out there is that if you roll it, you put the mix down, you don't roll it very well. It's got more than 10% air voids in it when you're done. Then what that does is it's kind of a two-factor thing. First of all, the mix isn't as stiff as it could be, but then you're allowing oxygen to get into it more easily, and so it's oxidizing and it's getting stiffer overall as it ages, and it's losing its viscoelastic nature. So now you've got a material that it's become stiff because of allowing this permeability, for allowing it to oxidize like it does. If you can reduce the oxidation that occurs, that can help overall with what your asphalt binder, how it's going to stiffen up and how the mixture itself is going to stiffen up. It's one of the reasons why I think, we've heard of the concept of SuperPay 5. There's been a number of people that have talked about that. But the idea being that you design it at 5% air voids in the laboratory, and then you compact it to 5% air voids in the field. So you've got a mix and maybe doesn't have as high of an asphalt content as what you normally would put in it, which would be bad normally for fatigue. But if you compact it enough in the field, you reduce the ability for it to oxidize as it comes down, and so that lesser asphalt content volume doesn't play as big of a role. So that's why I say these are all kind of interrelated, and all you really can do is control the properties in a specification, in a binder specification, is control the properties of the binder. Ultimately, balanced mix design, if that's where your criteria is leading you to, then that's what can control, and you can decide, okay, well, what's the right parameters for that, and what should that look like?
Well, following to that, I have a last question here, Mike. So is the intermediate PG temperature being overlooked, and is it becoming more relevant now with the adoption, as you mentioned, of the balanced mix design?
I think it is becoming a little more relevant. Yeah. It pretty much goes, it's rare, or at least we used to see this, that it would be, what controlled the low temperature grade and what controlled the grade of the binder was the high temperature grade and the low temperature grade. So if whatever your BBR stiffness and M value was, whatever your original or RTFO DSR was, those two things would control, and you would check it at intermediate temperatures, but it would meet, most of the time. There are a few exceptions to that. Oddly enough, it was the materials that actually had a better phase angle, those that had better viscoelastic properties, if you will, more viscous type behavior. Those might be the ones that would have trouble at intermediate temperatures. But that was the parameters as they existed within the PG system. So largely it was high temperature and low temperature that kind of controlled. But there is a greater focus now on intermediate temperature cracking. There is more interest in durability cracking. I think that's ultimately what led to the 9-59 and 9-60 research projects.
So I have more questions coming in. Looks
Okay.
like the more you answer, the more you prompt more questions.
I know. So I need to stop talking, is what you're saying.
Well, this is great. I think this is great. But one of the question is again related to using the high recycled material, whether it's RAP or RAS, by allowing some binder replacement up in the 30 to 40%. And I think the concern is that with the long-term, durability issues that may not show up on the PAV, DSR, BBR, or even the mixture testing, like the ideal CT or the maybe the Hamburg wheel tracking test. So the question is basically whether there is any research plan to find mitigation strategies for these concerns. So there's a binder testing from one side that also you may not be able to capture that. But also if you switch that to the mix and you try to focus everything on the balanced mix design, there are also some limitations on some of those tests.
Yeah, it's a good point. One of the things that just kind of previewed that both the 9-59 and somewhat the 9-60 research is looking at is having two parameters at intermediate temperatures. And I think part of that comes from the fact that we have to recognize that cracking at intermediate temperatures really is complex. It's more than one thing. And if you're trying to mitigate against that, it really matters whether you're talking about fatigue cracking or whether you're talking about, I'll use the phrase durability cracking, but it could be weathering, it could be loss of ductility, whatever you want to call it. Those are kind of different things. So if you're choosing to just use a single cracking test, I don't know whether that can tell you everything that you need to know. You need to kind of do the work and correlate that and see, okay, how does it reflect some of these changes in what we see? So I'll reference a paper that Wes Cooper at our place in Aguador presented at CTAA last year that looked at a cracking study we did, and it was really kind of a simple little cracking study. But what was unique about it, and we'll see this, and I think it's in some of the future work that I'm going to present. What was unique about it was we had a couple binders that looked to have very similar properties, except they differed in one area. And you could see a difference in what the CT index values were. It wasn't like a wild difference or anything along those lines. And you could argue that it would even be within testing variability, but it was enough to indicate that, okay, perhaps it does pick up on part of that. We know that CT index picks up on stiffness. That's part of it, but how does it do in regards to picking up on something like relaxation? And so that's a question that, that comes up. How does it characterize the materials? If you choose a test like the Texas overlay test, it's a really high strain test. So you might rank order your materials a little differently than if you chose a test like the flexural beam fatigue test and you ran it at a low strain, like 400 microstrain. You might get a different rank order because it's different sorts of cracking mechanisms that perhaps you're looking at. So I think that's where some of the challenge is whenever we talk about just choosing a cracking test within a balanced mix design environment. You kind of have to know what cracking you're focused on, what's the most important, and how is that test going to pick up on the relevant parameters that you think are going to be important to both fatigue cracking and perhaps durability cracking.
Very good. So obviously there's so many other factors that will influence the fatigue resistance of an asphalt mixtures.
Right.
One of them, and I think also you noted very well, Mike, that you need to start with good or decent components so that you can make out of them, a good, well-performing asphalt mixtures. I think, okay, I got one more question came in. We'll take that, I think. And then do you have an estimate of how many state highway agencies have adopted the recommendations for changing the G-star sign delta from 5,000 to 6,000 with a 42 degrees or greater?
I don't have an estimate of the agencies. It was adopted by AASHTO M320 just a few years ago. And so a lot of it, I guess, depends on, if the agencies are using AASHTO M320 as is, or whether they've got some modifications within their specifications. I'd probably have to go through, we've got a specification database that's on our website that I could look through individually with the states and just see what adoption looks like. But I would think most of them, if they are following AASHTO M320, would have made that adoption.
Very good. Thank you, Mike. We appreciate your time. We appreciate your insight and all the, what you do, and then great background, learning about the history and then
Yeah.
what's next. So
Yeah.
what
I
next?
should have mentioned, I'm sorry, Ellie, I forgot to mention, there is a survey that should be available. I guess that's going to be, is that in the chat box now?
Yes, it is. Thank
Okay.
you. Thank you, Mike. And then we encourage you to join us in a couple weeks on November 20 for the part 2 of this presentation. And yes, the webinar recordings will be available in about 2 to 3 weeks, and those will be posted on the website, the AIEI website through UNR, as well as on our new YouTube channel, where we have all those different past webinars and some other resources for you. So please subscribe to our YouTube channel, and then we'll see you in a couple of weeks. Thank you very much.